Hello everyone and welcome to this year's special AP Statistics practice test review. So the College Board announced that because the test is take-home this year, students could use online calculators. We're going to use ClassCalc because it's free, so it's easily accessible to all of our viewers. You can just go to classcalc.com/graphing and it'll be right there. And it has tons of powerful statistical features that you need for an AP test, like distributions, and then hypothesis and statistical testing. And if you'd like to follow along with a different calculator, the experience won't be so different. So if you have like a TI or a Casio or something like that, you're welcome to use that as well and follow along. So the information provided us by College Board at this time is that right here. Actually, that's the most important piece of information. There will not be an investigative task on the 2020 AP Statistics exam, which is usually question 6 on the exam. So to get as close as possible to what we might be able to expect, we're going to use the 2019 exam. We're going to go over the 2019 free response questions, and we're going to skip question 6. All right, let's get started with today's test. So this is the 2019 AP Statistics exam. And in question 1, it asks, the size in square feet of the 20 rooms in a student's residence hall at a certain university are summarized with the below histogram. They give us this little histogram over here. And they say, based on the histogram, write a few sentences describing the distribution of room size in the residence hall. So when describing a histogram, we want to give 3 details. We want to give the shape, the center, and the spread. So the shape, as you may have guessed, is going to be, and I'm not going to write the whole sentences here just because it's going to be tough to write on the computer, but the shape is going to be bimodal, right? And you could give more details saying, for example, the 2 peaks are concentrated from 100 to 200 and from 250 to 350, right? So that's going to be the shape. The center is going to be, right, obviously between 200 and 250. That's pretty clear based on the data. Go the opposite direction here. That's fine. And lastly, we got to give the spread, which can be given as the IQR or the range. But because we don't know necessarily the minimum and maximum value here, we can't just say 350 minus 100. It's going to be between 350 minus 100, which is going to be 250, and potentially 300 minus 150, which is 150. So between 250 and 150, or probably 150 to 250. All right, now in question number 2, they give us some summary statistics, and they say, all right, well, tell us if there are any outliers. So to solve this question, we're going to need 2 things. First, we're going to need to take Q1, and to find the lower boundary of our potential outlier range, it's going to be Q1 minus 1.5 times the IQR. And to find the upper boundary, it's going to be Q3 plus 1.5 times IQR, right? So we'll bring out our handy ClassCalc calculator. And what I like to do is I actually like to set these things with variables. So I'm going to set the interquartile range using Q. I'm going to set that to equal 292, which is our Q3, minus 174. That's going to be 118. And so now we'll do Q1, which is 174 minus 1.5, typing correctly today, times Q. And we'll set our, wow, keep typing 175 instead of 4. There we go, negative 3. And we'll do our Q3, which is 292 plus 1.5 times Q, right? And as you can see, the lower bound here is going to be negative 3. The upper bound is going to be 469. So we don't have any numbers less than negative 3 or greater than 469 because our min is 134 and our max is 315. So there are not going to be any outliers. And then in the next part, they say, then use the following grid to sketch a box plot of the room size. So now we're going to just sketch a simple box plot. And what we need for that, we already have. We need the min, Q1, the median, Q3, and the max. So we're going to set our line on the min, which is going to be right around here, 134. Right? This might be a little wiggly because I'm using a computer keyboard. And then we're going to start our box at the min. So that's going to be at sorry, we're going to start our box at the Q1, which is going to be at 174. So right around here is the box. Beginning of the box, and that should be a straight line. And then we're going to draw the median at 253. So median at 253. The Q3 at 292. Here. And then the max at 315, which can be right around here. So that line will connect there, and then these three are going to be our box right there. That's it, simple that. We have a box plot. And the last question is, what characteristic of the shape of the distribution of the room size is apparent from the histogram but not from the box plot? And you kind of eyeball the two, and I mean, what automatically jumps at you is clearly this is bimodal. You couldn't tell that this is a bimodal distribution here. That'd be you wouldn't be able to tell that from this data. So that's the answer, right? That it's a bimodal distribution. I'll just go ahead and write that down. You guys can write that down in full sentences. And quick note on the AP test: it's never good to write redundant information. It's definitely good to write in full sentences. And if any information is relevant and true, relevant to the answer and true, it's always a good idea to include. All right, so this question basically asks, about some researchers that are investigating how, fungus will affect the spread of some insect, right? And they have 4 different concentrations of fungus mixture: 0, 1.25, 2.5, and 3.75. And an equal number of insects are basically placed into 20 individual containers, and they spray it with one of the 4 mixtures of fungus, and then they measure after 1 week. They record the number of insects alive, right? And so if less insects are alive, that means the fungus is working. So the first part asks us to identify the treatment, the experimental units, and the response variable of the experiment. And remember, if you can give relevant information, that's true, you should. And numerical values, where appropriate, should be included. So some sort of quantitative, sorry, not numerical, but some sort of quantitative value. So for example, for treatment, we know our treatment is the spray, but we want to say, the 4 different sprays that contain, 0 milliliters per liter, 1.25, 2.5, and 3.75. For experimental units, we want to say the 20 individual containers containing the insects and the combination of the insects and the treatment. And then for the response variable, we want to say, we don't have a specific number, but we want to say it's the number of insects counted in each container after a week. So for the second part, it asks, does the experiment have a control group? And the answer is yes, because in this case, 0 milliliters, and you want to include that you for sure want to say that it's the 0 milliliters per liter spray that is the control, right? And that's because the thing you're measuring, right, the treatment is the fungal spray. So if it doesn't have any fungus, that could count as a control. And then the third part asks us to describe how the treatment can be randomly assigned to the experimental unit so that each treatment has the same number of units. So that's really important. You can't just use like a random number generator and say, well, if it's this number, then it'll be this, then it'll be this treatment, because that might end up in some, it's like flipping a coin. You might flip it 10 times and get 6 heads instead of, you won't necessarily get 5. So you can't just, you gotta make sure that it ends up results in the same number, or that each of the 4 treatments are evenly distributed amongst the 20 containers. So one way to do it would be to just you want to include that you're going to label the containers, right? Because you can't assign it directly. So you have your 20 different containers, and you're going to label each one of them maybe 1 through 20, and then you'll use some sort of generator that says, all right, these 5 numbers are going to be, these 5 random numbers are going to be 0 milliliters per liter. These 5 random numbers are going to be 1.25. The other 5 is going to be 2.5, and the last 5 is going to be 3.75. And probably a good idea to include that the random number generator doesn't repeat at all, right? So that each of the 4 treatments has exactly is assigned to 5 of the 20 individual containers. All right, now question 3 here gives us a table of men versus women, and whether they take their medicines never, sometimes, or always. They ask us a bunch of probability-related questions about it, so let's jump right into it. What is the probability that the person selected will be someone whose response is never and who is a woman? So that's going to be an AND probability, right? So it's got to be an intersection of both. So never, right? And woman, that's going to be this one right here. So the answer is going to be 0.0636. Next one says, what is the probability that a person selected will be someone whose response is never or who is a woman? So sorry, the emphasis should be on the or, right? Never or is a woman, right? So that's going to be, sorry about that. That's going to be either that they're never, right? Or that they're a woman. So you got to add these two. But if you notice that both the total here and the total here take this square right here into consideration. So you got to subtract that out once, right? So it's going to be, it's going to be a 0.1200 plus 0.5300 minus 0.0636. That's going to be equal to 0.12 plus 0.53 minus 0.0636, 0.5864 should be the answer here. Great, and then what is the probability that the person selected will be someone whose response is never, given that they're a woman, right? So now it's given that we're in this category, what is the probability that the chance will be never? There are two ways to think about this. We could say, all right, well, we're just considering this category, so this is our new total, right? So it's just going to be, you know, the probability of the thing we're looking for over the total. So 0.0636 over 0.53, right? But if you notice, that also ends up being the equation, right? So P never given woman, right? Wham. Equals P never and woman over P woman. And that's exactly what we have here, right? So this is going to be 0.0636 represents P never and woman, and 0.53 represents P woman, right? That's going to give us, let's check that real quick, 0.0636 over 0.53. Correct answer of 0.12. Sorry, we're getting off to the side over here. All right, for the people surveyed, are the events of being a person whose response is never and being a woman independent? We should do this one in red. Why not? So we want to find that P never and P woman are independent, right? And the way to find that is to say, well, you know, if they're not independent, right, then P never given you're a woman. So if you're a woman, the probability of being in the never category should not be equal to P never, right? They should be different, right? Should be somehow dependent. And we calculate P never given a woman, and P never. So P never is going to be 0.12. We already know that, right? And then P never, we're going to drag that over here. P never, given that it's a woman, right, is going to be, oh, we already solved it earlier, never mind. So you can see that's 0.12 as well. Wow, they walk us through it, it's so nice of them. So because that statement is not correct, because they are equal, right, then you know it's independent, right? Whether you're a woman or not doesn't affect the probability of you being in the never category. And now we have for C, it asks us, you know, you have a large population, and, you know, assume the probability that a person will always, they'll be in the always category, take the medicine that's prescribed is 0.54. If 5 people are selected at random from the population, what is the probability that at least 4 of the people, so at least, right, so that's important right there, 4 of the people will be selected will always take the medicine as prescribed, right? So the probability of success is 0.54, right? And we want to know that 4 or 5 people basically, if selected at random, will be of the people that always take medicine. So there is a longish way to do this, right? The way to think about it is it's a binomial distribution with you know, n equals 5, so 5 trials, and p success equals 0.54, right? And so you can do, you could do it sort of ish the long way, where you actually draw out the binomial distribution formula, and you do the combination, and 0.54 to the fourth, and probability of failure will be 0.46 to the one. And then you do it, that's the probability that you have 4 successes, right? And then you add the probability that there's 5 successes, right? That's going to be 0.54 times 0.54 to the fifth, and then times 0.46 to the 0, which is going to be 1. I actually prefer, because it's quicker, and at least in my mind, it feels like at least I'm getting the feedback that I'm doing the right thing. And I like when I have that in a math test. So I don't have to think about this problem anymore, because I know I got it right either visually or somehow else. I justified it, not just in numbers. That for me feels really good, because then I can just move on from that problem and not look back on it if, say, I have more time. So I would just do binomial distribution and grab the CDF. So with ClassCalc, you can just go to stats, distribution plots. We got the binomial distribution right here. And as we said, it's 5 trials with a 0.54 chance of success. And if you click that magnifying glass, it'll blow it up. And then we just grab the CDF from 4 to 5. And that actually gives us the correct answer, which is 0.2414, 0.2415, I guess, to round it up. So if you work this out, you get 0.2415. Which is the correct answer. All right, so in this question, we're presented with this plant called Kochia, or I don't know how to let's just call it K, whatever. And scientists are concerned that it's becoming resistant to an herbicide known as glyphosate. So that's what we're going to be exploring, right? And we don't want them to be resistant, is the idea. So in 2014, 19.7% of 61 randomly selected plants were resistant, right? And then so we have 2014, we have 19.7% of 61 are resistant. And then in 2017, right, we have the information that 38.5% of 52 randomly selected plants were resistant. And, they're asking us to somehow present, probably through a statistical test at an alpha of 0.05, to prove whether or not there has been an increase in the proportion of resistance to glyphosate. So, in this question, we want to give a really descriptive answer. We don't want to just run a hypothesis test and then say, or run a statistical test and just say yes, no. We actually want to walk the reader through how we're thinking, right? So we'll start off with, discussing, there's a couple points we want to hit. We want to, first of all, set up a null and alternative hypothesis. And then we also want to mention specifically that we're measuring a proportion, and explicitly say what the proportion is that we're measuring, and then explain what statistical test we'll be using, what hypothesis test we'll be using, and then finally execute that test. So we can call the proportion of resistance in 2014 and 2017 P14 and P17. So that's the first thing we define, right? We actually want to walk them through our thinking. So we'd say, P14 and P17 represent resistance during or from the 2014 and 2014 and 2017 sample. And then we would set up our null and alternative hypothesis. So our null hypothesis is that P17 is equal to P14, right? So, and we want to say, sorry, this is actually incorrect, right? So we want to say proportion, right? We want to specifically explain proportion of plants resistant to the glyphosate herbicide during the 2014-2017 year. The null hypothesis would be that the proportion the proportion of resistant plants in the 2017 year would be equal to the proportion of resistant plants in the 2014 year. And then the alternative hypothesis, right, would be that P17 is greater than P14. And lastly, we'd want to identify what statistical test we'll be using to prove or disprove this the alternative, or to accept or reject the alternative. And you could see that we're basically comparing the proportion from two samples. So that's going to be a 2-prob-z test, which you can do by hand or use the calculator, as we will. Now, the second part of the problem actually has too many parts. One is checking the conditions for executing our 2-prob-z test, and the second is to actually execute it. So in the first part, so we'll call that 2A, right? What we want to do is we want to check that the sample is randomly selected. We want to check that it's approximately normal, and then we also want to check that the samples are independent. So for let's go with A, B, C. For randomness, right, you can actually, pretty sure in the problem, so you can actually look in the problem, I believe they say right here, right, that they're randomly selected, so that actually takes care of that. For independence, right, the way we prove this is we'd say, well, the population is sufficiently large such that one sample or one trial does not affect the other. And it's reasonable to assume that the numbers we're given here, which is 61 plants in 2014 and 52 plants in 2017, that's going to be considerably less than 10% of all plants grown in that year. So we can assume independence, right? So we have randomness, we have independence. And then C, this is the one that requires the most work, not a lot, but requires the most work, is checking for randomness. So we would want, we would want to calculate the proportions of failures and successes in 2014 and 2017, and make sure we can expect at least 10 failures and 10 successes to assume normality, right? So we want to check for normality. I don't know if I mentioned that at first, but that's what we're checking for in the third one, right? And so to do that, right, we would take P of 2014, right, and then we'll set that to 0.197 times 61, right, and then Q of 2014 is going to be equal to, let's move a little down here, 0.803 times 61, right, so, or 1 minus P, right? And then P of 2017 is going to equal 0.385, 38.5%, 385 times 52. And then Q of 2017, and all of these need to hopefully be greater than 10, is the assumption we're checking here. Is going to be 0.615 times 52. And I won't bore you plugging these all into the calculator. I've already done it beforehand, and that's going to be, we're going to get 12.017 here. We're going to get 48.983 here. We're going to get 20.02 here. And we're going to get 31.98 here. And so these are all greater than 10, so we've got to check by the normality as well. And the final part, so part 2B, and we can do that right here, is just to set up the test and then get an answer from your calculator. And it's probably important to explain what the results of the test are in terms of your alternative and your null hypothesis. So now we run our 2-prob-z test, right? I'll just call that 2PZT, right? So now we'll go ahead and open our calculator, and we'll grab the 2-prob-z test, which is going to be right here, 2-prob-z test. And note that ClassCalc gives first x1, x2, then n1, n2, unlike, for example, the TI that does x1, n1, x2, n2. In this case, because we're checking for the proportion of 2017 being greater than the proportion of 2014, 2017 year will actually be our x1. So go ahead and plug our numbers in, and that'll give us 2-prob-z test of 20, 12, 52, 61. So again, 20 20 quote unquote successes out of 52 for 2017, and then 12 out of 61 for 2014. And that gives us a z-score right here of 2.209. We'll want to write that down, and a p-value of 0.013. Again, because we're checking for 2017, about probability of the proportion of 2017 being greater than 2014. And based on our value we see here, we know that that's less than our alpha value of 0.05. So we can reject the null and assume that there is a difference between the proportions of our samples. So we'll go ahead and write that down. So 2.209 for the z value. And our p-value was 0.0136, let's say. We could actually say p that the proportion of 2017, let's cross that out. P that the proportion of 2017, oh, P17 we already named, is greater than P14, right? Again, good to be explicit if you can be, is going to be 0.0136. And then we'll say since, since 0.0136 is less than alpha, then reject the null. All right, now in number 5, we basically have a problem where you have this normal distribution for the lifespan of a battery for a phone, and we're saying it's, again, it's approximately normal with a 30-month mean and a standard deviation of 8 months. And then they're saying that the company for $50 offers a 2-year warranty on the battery. They would replace it within 24 months. So the first question says, in how many months from the date of purchase is it expected that the 25% of batteries will no longer work, right? And so this is, in this problem we have a normal distribution, right? There's my little bell curve. We got a mean of 30, right, and a standard deviation of 8 months, right? And they're saying, all right, well, what does the left 25% look like? Like what value over here, right, will give me, what value do I have to put here to get all the phones, right, in this distribution that their battery would die, the lower 25% bound of that, right? So what value here to the left of that, to the left of that value needs to cover 25% of all the possibilities, right? And as you can tell from this problem, it's an inverse CDF type of problem, right? So it's like, instead of for CDF where you give it the bounds and it gives you the area, here they're giving us the area and it gives us the bounds. Now there's a way to do this manually, but we're going to use the calculator here because it's just quicker and it'll save you time. Remember, if you're going to use the calculator, make sure to really explain what you're doing, right? So to make sure to explain why, you explain everything up to the calculator, and then right here what function you put in the calculator. So you would write, I did inverse, CDF of 0.25, right? And so we're going to go ahead and do that on ClassCalc now. So we'll open up so the way we do it here is we first type in a distribution. So that's the normal distribution right there. And we'll do 30 is the mean, and 30 is the mean, and 8 is a standard deviation. And it actually gives us the normal distribution right here, there we go, which is nice and easy, and you can look at it. And then we'll do the inverse CDF. So to get the inverse CDF, you then kind of attach it to the end. So we'll grab the inverse CDF right here, and we'll put 0.25, and that will give us 24.60, right? And so that's the value we're looking for here, right? So by the 24.60th month, right, you would expect that 25% covers about 25% of the area of the normal curve. So there's 25% of the batteries in the phones will have died by then. And so part B says, suppose one customer who purchase a warranty selected at random, right? What is the probability that the customer will acquire a replacement within 24 months? So now we're actually doing a CDF again, right? So we have a normal distribution. And the buck log looks different this time, but it's the same. And we're saying, all right, well, here's the X value of 24, right? 24 months, and what area, right, does that correspond to, right? So what percent, right, or what is the probability, sorry, that a phone battery will die before 24 months? And so now we could just go back to the normal distribution, and we could actually just go ahead and delete this part right here, right? And we can grab a CDF and take that from negative infinity to 24. And that is going to give us 22.663%, right? So we go back here, and we get 22.663%. And again, when you're using the calculator, you don't want to just write down the answer. You want to give them as much of your thought as possible. So write down this curve, show the area, and then maybe write in the function that you use. So normal, normal dist. That's the way it looks like in ClassCalc. 30, 8, and then you could say like CDF, right? I can't really fit that in here, but CDF negative infinity to 24, and then you could say equals, sorry, I'm really squeezing it in there, but you could say equals 22.663%. And then the final part says the company gains basically $50 for each customer who purchases a warranty and does not end up needing a replacement, right? And then the company loses $150 for each customer that purchases a warranty and then does end up needing a replacement, right? Because you end up having to replace their battery, right? So the more customers, right? The idea being that the more customers who buy the warranty but don't end up needing a replacement, the more money the company makes, and that's how they're doing their math. So what is the expected value of the gain for the company for each warranty purchased, right? And so the expected gain is going to be each value multiplied by its probability. That's just what you're going to expect the average gain to be for each value. And so that's going to be $50 or whatever. We don't need units. 50. Well, maybe you do, but 50 times the probability that the lifespan is greater than 24, right? Plus. And then here you're going to lose $150 times the probability that the lifespan is less than or equal to 24. And we already got the probability that the lifespan is less than or equal to 24 right over here, and that's going to be 0.2266, right? So that's going to be negative 150 times 0.2266, and then this is going to be the 1 minus that, right? So that's going to be 0.7734. So we'll grab our calculator again real quick. Get to this side. So the expected gain is going to be $4.68, which means it is a profitable move for them. There's our answer. And so that's it for today's practice test. This is my first video ever doing something like this. So if you guys, I really want feedback. So if you guys have any questions about how I figured something out, or if I skipped any steps, or if I missed anything, it is possible that I missed something, that I didn't go over it enough, and I totally appreciate the feedback. So feel free to let me know in the comments below. Feel free to message me if you want, and if I could be of any help, let me know. And then also, if there's other content that you guys want me to cover, a specific AP problem in statistics, or any other subject, physics, calculus, whatever you need, become me as your free personal tutor. I'm happy to make videos about them and throw them up online. And if any of you guys want the link to the calculator, it's a free calculator, and you can use it on this year's AP test, and it'll probably be pretty helpful, especially for those of you who don't want to buy a $100 graphing calculator. Not that you need to. Then I will link that below. But I hope you guys enjoyed.